I'm Ben. I'm a second-year PhD student at the University of Oxford in the AIM CDT. I'm supervised by Xiaowen Dong in the Networks and Society group, as well as Michael Bronstein. And here today, thanks for inviting me, by the way. I'm here to present our paper, which just got accepted at ICML 2023, DRew, Dynamically Rewired Message Passing with Delay, which I worked on with Xiaowen and Michael, and also Francesco, who is a postdoc at Cambridge. Right, so there we go. Right, so general overview of what I'm going to talk about. I'll give a little bit of background on like message passing neural networks and particularly long-range interactions, which is kind of the main use case of this framework. Talk about our two main contributions. Firstly, dynamically rewired message passing, and then the secondary contribution, which is delay, specifically delayed dynamically rewired message passing. Then I'll talk a little bit about why DRew works theoretically and give some experimental results, and then a little bit about future work. Right, so quick overview of message passing. I suspect most people here are probably aware already. Message passing neural networks are by far the most popular graph neural network paradigm, and generally they consist of essentially one hop aggregations. There's a few different varieties. The most sort of complicated being like full message passing, and then convolutional ones like GCNs and GIN kind of fit within this framework. But generally, they all consist of the same thing of having an aggregation step over one hop followed by an update step. This comes with some problems, particularly for the case of long-range dependencies. So just to explain what long-range dependencies means. This is essentially tasks where the output of an MPNN depends on distant nodes interacting with each other. And I'll come back to this slide in a minute, but just a quick aside on long-range interactions. This is an area which has become a fair bit more popular in quite recently, particularly with the release of the long-range graph benchmark set of datasets. And you can sort of see why this is becoming an area of interest. Quite a lot of real-world applications which rely on sort of global graph information or rely on distant node interactions. A good example of this being like in molecules, where you can't necessarily represent with a graph the 3D interactions between sort of distant molecules. And you can kind of also look at the recent bunch of papers relating to this and using LRGB to sort of motivate, okay, this is a problem that people are interested in. People are interested in solving this problem of long-range interactions, especially as popular graph data sets are getting bigger and bigger, like PCQM4 and stuff. There's a case to be made that large data sets in themselves might exhibit some degree of long-range interaction. So with that sort of motivation, so we have this problem of long-range dependencies, and classical MPNNs, these one-hop MPNNs, struggle with tasks that require long-range dependencies, and because of two general issues. One is over-smoothing, which is where this occurs essentially because you can think of a message passing layer as a sort of a smoothing operator, as like a convolutional smoothing operator, which means that if you stack lots and lots of these layers together, you end up with homogeneous node features. Because classical MPNNs only propagate one hop at a time, if you have long-range interactions, say you have node I and node J that have to interact, you need to have, and those two nodes are R hops apart, you need at minimum R layers in your MPNN in order for them to interact. So if R is large, you need a lot of layers, and you end up with this over-smoothing problem where lots of subsequent convolutions smooths out the node features. The other problem is over-squashing, which is essentially because of information bottlenecks in graphs, where basically as model depth increases and long-range interactions are more required, you essentially have an exponentially growing amount of information that is forced to squeeze into the same fixed size node features. So we have these two problems, and both of them are exacerbated by having to go deeper, which is a necessity in long-range interactions and for long-range tasks. sorry, I'm not skipping for some reason. Okay, there we go. Right, so a few different works have sort of tried to address this problem, and we are thinking of basically all of them under the broad umbrella of graph rewiring. And I'd like to make clear here, sort of there are two sort of types of graph rewiring that we're thinking about. The first is static graph rewiring, which I think probably most people would think is what they would think of as graph rewiring, which is essentially where you rewire the graph as a pre-processing step. You alter the graph topology itself to make it more friendly, more amenable to analysis. And this probably consists of dropping or adding nodes or edges. Might consist of adding a global node or adding fully adjacent layers. Some kind of rewiring according to some connectivity measure like Diggle and stochastic, like Ricci flows would fall into this. And I'm also putting in positional encoding because, again, it's a sort of global layer. Contrary to these methods, we are sort of more focused in this paper on what we're calling computational graph rewiring, where essentially rather than changing the input graph itself, you're changing the way you allow information to propagate during the message passing. So essentially you can think of it as like when we're performing a message passing layer, we're kind of adding edges to the graph along which we allow information to propagate. And in this way, we can sort of think of this as a form of graph rewiring. So this is sort of the general proposal for what our framework is kind of hoping to achieve. We have transformers, which is one. Did I mention this? Oh yeah, sorry. I meant to mention that. Yeah, under this umbrella of computational graph rewiring, we have two main things. One is graph transformers, which are very popular at the moment and seem to be kind of accepted as the go-to model to use on long-range tasks and big graphs, because they allow all nodes to interact with each other, because they just throw the graph topology away and connect all pairs of nodes together. And kind of similar to this is multi-hop MPNNs, which kind of are a sort of middle ground between classical MPNNs and transformers, where you essentially allow aggregation over multiple different adjacency matrices. Which might be powers of the adjacency matrix, or it might be like shortest path, one hop, two hop, three hop, etc., like shortest path adjacency matrices. But the problem with these are, firstly, transformers, since we're just connecting all nodes together, we are basically just throwing away the graph topology. That's a nice bit of inductive bias that we would like to use, and that we suspect we know is useful, and it's just sort of being thrown away because transformers happen to work quite well. And multi-hop MPNNs kind of have a similar problem. Like the way most of them work, and we kind of have a diagram to demonstrate this, is that you essentially just densify the computational graph, like rather than allowing in a classical MPNN allowing like one hop aggregation per layer, you effectively just add new edges up to 1, 2, 3, however many hops you choose, and this can be as many as like 10 or something, which essentially is just a slightly sparser version of a transformer. You're still connecting nodes that are quite distant from each other. You're still letting them all aggregate at once, and if anything, this is probably likely to contribute even more to oversmoothing and oversquashing, because you're trying to aggregate so many nodes at once, like directly from the first layer. And the other problem with multi-hop MPNNs, or at least we sort of assert that it would be a good thing if they had this, was that if you just add these extra edges from the very first layer, you're losing this additional inductive bias of the idea of information flowing through the graph. So in a classical MPNN, two nodes that are R hops apart will interact with each other after R layers. So you can kind of think of this as it takes R time steps for the information to reach. We can think of this as an idea of information flowing. And when you have a multi-hop MPNN, you kind of lose this bias. Things can just connect immediately. So armed with these two inductive biases, how can we come up with a framework to exploit them? And so yeah, the intuition here for dynamic rewiring is sort of these two things. One is that we think that nodes that are closer together should interact earlier in the architecture, which is what classical MPNNs do, and transformers and multi-hop MPNNs don't do. And also just sort of, well, more generally, we argue that it's not simply how two node states interact with each other, but also when that happens that is important. So I'll explain that better in a minute when we get into actually explaining the model. But first, just background for notation. For pretty standard representation of an MPNN here with a one-hop aggregation. Couple of things I want to particularly point out. One is this k-hop neighborhood notation. This just refers to the adjacent, well, this just refers to the neighborhood of a node I according to its shortest path distance, and which we are defining here by dg as, just the shortest path distance or geodesic distance between nodes on the graph. So in this case, classical MPNN is always a one-hop aggregation. So with that in mind, this is our, to start with, before introducing delay, this is just the more basic dynamically rewired MPNN framework. And I've put the vanilla MPNN here for comparison. But essentially the differences here are, firstly, that we have a separate aggregation k for each k-hop distance, which in many ways is quite similar to other multi-hop MPNNs. But the main difference is we essentially add a new sort of term to the multi-hop aggregation with each successive layer of the architecture. Which you can sort of see here. So, for example, the first layer of vDRew MPNN is just the same as a classical MPNN. But then in the second layer, you aggregate both the one-hop and the two-hop. And then in the third layer, you aggregate the one-hop, the two-hop, and the three-hop. And so essentially, each new layer is adding a new hop distance to the aggregation. And you can see here that we update with all of the, we get the aggregation separately, and then we update them together. So if this just reduces to vanilla MPNN if all of the k greater than 1 aggregations are just identity. Sort of give a sort of more intuitive explanation for this. You can sort of see on the left here, classical MPNN, and here we highlighted the node in blue to sort of show information flowing from that node to other nodes. And you can see in this one that information is flowing one hop at a time with each layer, and that's all it's doing. Versus the Drew MPNN, where you can see that in each successive layer we're adding a new set of edges for the new elf hop distance. Okay, so with that in mind, let's introduce delay. So now we've introduced Drew, we kind of have two ideas here. We have classical MPNNs in which we have nodes I and j which interact with a constant delay, i.e. node I doesn't see node j until r layers have passed, provided they are r hops apart. So the lag of information, if you think of it as like information from I taking time to reach j, the lag of information is always the same. And then we've just introduced Drew, where we have this new thing where nodes are interacting only from a certain depth of the architecture, but without any delay. So whereas for a regular MPNN, a certain amount of sort of local smoothing has happened. In Drew, a node is just seeing a node directly as it is at the current time step. So to try and introduce a sort of notion of sort of time and of information flowing through the graph over time, we asked this question: what if we consider the state of node j as it was when the information left it to flow towards I? And the way we kind of facilitate this is with this delay, sort of delay parameter nu. Well, the delay parameter is tau. Sorry, excuse me. The delay is tau, and we have a hyperparameter nu, which is we sort of use to control the rate of delay, as it were, which I'll get more into in a minute. So this is essentially identical to previous Drew, with the difference being that now for each k-hop aggregation, the node features that are seen, as in of node I, its k-hop neighborhood nodes j are seen with a delay. The delay being node I sees node j as it was a certain number of time steps ago. Here, where time steps means layers in the architecture. Again, we've got sort of graphical representation of this. So again, we have regular MPNN and Drew, and then over here we have Drew with delay. Here, where nu equals 1 represents full delay and nu equals infinity represents no delay. I'll explain that better in a second. But essentially, you can see here that the same idea of like information flowing from the highlighted node. You can see that we're still adding each sort of k-hop distance with each layer, but rather than seeing a node as it is in the current time step, you see a node as it was a number of time steps ago equal to the hop distance. So for instance, if you're in the, if it's two, if you're in the second layer, you see a node that is 2 hops away as it was 2 time steps ago, and so on like that. And we sort of think a good way of thinking about this is, I see a hand. Yes.
Yeah, go ahead, finish the slide. Yeah.
Oh, sure. Yeah, we have a sort of way of thinking about this that we think is maybe a little bit clearer, which is thinking of Andrew, which is what we call it with the new Andrew, as distance-aware skip connections. So if you traditionally skip connections in GNNs, you have like a single, just a single layer back, and also just connect a node I to itself at the previous layer. And we can think of Andrew here as allowing sort of skip connections, sort of both like horizontally, as it were, within the same sort of slice within the same layer, and also vertically to previous layers, and not just between the same nodes. Essentially, yeah, so essentially you can think of it as being skip connections between separate nodes with like sort of various amounts of skipping different layers based on the distance between the 2 nodes on the graph. Yeah, a couple of questions. Should we do those?
Yeah, so I think it's a really interesting approach. Like one can see that suppose you have a merchant that sells apples, and he wants to find someone who wants to eat apples. So what happens is he starts a random walk by GNN layers. So like first layer, second layer, third layer, fourth layer, he finally found someone that wants to eat an apple, and then do the transaction directly with that person. That's kind of the approach that you're doing. Whether if you didn't do that delay, what would happen is that the person who wants to eat an apple because all his neighbors are not hungry, then he would have oversmoothed, and by the time that the merchant arrives there, he's going to say, I'm not hungry anymore. So the idea of this delay is that you can then do search and transaction. In my opinion, like that's the way I view it. Like you first search and then you transact directly once you find it with the state that you wanted to transact with to begin with. So yeah, I don't know if that makes sense to you, and you'd like to add to that.
Yes, it's not how I have been thinking about it, but I like an alternative perspective, and yeah, that sounds like a pretty good explanation to me. Yeah, I might have to work that in next time I do a talk like this.
Yeah, I guess
Dennis, or
when
sorry,
you yeah, it's like when you introduce these kind of concepts, like it's good to have analogies on like what happens, so like and why there's an advantage to that. Yeah, but if you come up with additional analogies, I'm happy to hear them. Dennis, go ahead.
Yeah, thank you. And just to add to what Dominique said, this is also correct. I think that for classical MPNN, while it is true that the information from the node I to the node J on the distance R flows after R steps, but it is also true that the nodes in the vicinity of J, they know about J in beforehand, right? Because information flows obviously from every node. So because of that, they kind of, it's not really an autoregressive problem in some sense, because they are already a bit oversmoothed with what J represents, if I see it right. And because of that, there might be some like premature interaction with transaction in some sort becomes a bit cute, I think.
If I understand you, I think so. Yes. So firstly, I'll sort of say that we have this this notion of delay, which comes from this new hyperparameter, which we essentially kind of use as a way of sort of controlling like the rate of delay. So yes, there is some like depending on like what delay you choose, there is kind of some delay, some degree of kind of, what's the word? I suppose a sort of contamination or like a little bit of local smoothing. But you can kind of think of it as like you know, if you have if you have like more delay, like sort of full delay, which here is when you set new to being equal to 1, which is just where like 5 hops means 5 time step delay. You do keep this property of 2 nodes only interacting, 2 r-distant nodes only interacting at all once they after r time steps. But then if you use less delay, you get sort of more local smoothing when that interaction happens. So in this way, you can kind of use it to control. Oh, go on.
No, this I understand. Actually, I meant for the classical message passing neural network, because even there, isn't that right that after, let's say the distance is 10, after 5 steps, the intermediate node will get information from both the initial node, but also from the terminal node. And because of that, it sort of knows what is the transaction between the first node and the last node. Like it is already contaminated in that sense. Okay,
yes,
but actually, I just wanted, sorry for interrupting. I just wanted to ask a very basic question just to understand further. Is it true that in this Drew with delay, we need to keep intermediate representations of node embeddings on each layer step? So essentially,
yeah, I got it. Yeah, sorry, go on.
No, you can answer, please.
Yeah, so I was saying, yes, I got asked this when I talked about this last couple of weeks ago, and the answer is like probably no. You might get better performance or results if you don't necessarily always keep all of the intermediate results. This is not necessarily the most efficient model, and this is kind of what we're currently working on, is like methods to sort of make this more efficient. And yeah, there's a case to be made that like you might not be doing things in the most kind of information efficient way by holding on to all of these kind of intermediate representations, because you're kind of, you know, making a connection that you already kind of made in the previous layer. So yes, I think it's probably the case that this can be improved on, and that's something that we're sort of doing in follow-up work. But I guess the kind of idea of this was to sort of keep it kind of as like pure as possible, in the sense that you know, we just keep it to a framework where at least for the delay Drew, all nodes interact with a you know, hop distance according to sorry, they interact with a hop distance if that many layers have occurred, and they always interact with a delay equal to their distance. Sort of just keep it consistent, because we're interested in this idea of like how the information flows, and if you kind of start dropping these kind of intermediate elements, then you're kind of picking and choosing like how you want information to flow, rather than kind of being, I guess, democratic about it throughout the entire process, if that makes sense.
Yeah, and the mu is a hyperparameter that is chosen sort of before training. It is not adaptively chosen while training occurs.
That's correct. Yeah, it's at present anyway. Yeah, it's chosen. You choose it beforehand, and I've got some sort of examples later to kind of demonstrate how you might choose this. But essentially, yeah, you use it to kind of determine how sort of fast you want information to propagate through the graph. But yeah, I can explain that better in a little bit. No worries. Thanks for the question. Right. So yes, we have the notion of skip connect.
I have a question here, like why the delay is only on the like on the node that's k-hop away? Why not have a delay on both nodes, so that both of the nodes initial state communicate with each other? Or that would be back to the k-hop MPNN, right? If we do that, I guess.
I mean, I guess that would just essentially be like repeating a calculation that you did in a previous layer. would it not? I think the sort of idea is, for the source node, you want to think of it at the current time step that it's in, but since it's interacting with a node whose information started traveling towards it several time steps ago, when when that information sort of arrives at this node, it will be the same as it was when it left, if you know what I mean. Like we're kind of trying to avoid this intermediate mixing along the way, but we don't want to just see the node as it, we don't want to sort of skip over, or we don't want to kind of cheat and see it exactly as it is in the current time step without it having to go through the intermediate steps of traveling, or rather the sort of time of traveling. We want to facilitate this idea of like seeing as it was multiple time steps ago, like the time taken for it to travel without necessarily forcing it to mix during that time.
Yeah, okay, I see. And right now, like if you are at layer 4, for example, do you continue sending messages from every node that's at distance 3 and 2 and 1, or you only do? Okay. So
yeah. So at the moment,
it grows exponentially, kind of the.
Yes, it does. Which is why we have, and actually this kind of comes on to the next slide. So before was just sort of a general framework for applying Drew to MPNNs, and I want to note that Drew the framework is applicable to any MPNN, and sort of as an example, I've got a few particular instantiations here for some common MPNNs. These particularly are the ones that we use in the experiments in the paper. But yeah, I think it's worth drawing attention to the fact that a couple of these, or for GCN and GIN, we have separate weights. Or separate, we have separate weights for each k-hop and for each layer. So at least in sort of this first pass, it is quadratic scaling of the weights for these particular like instantiations. For gated, we found that we didn't need to do separate k-hops, and we could have shared weights across different k-hops, and that seems intuitively like to make sense to us, because you kind of have, since you have these sort of edge gates, as it's like anisotropic, you kind of have like a separate mixing for each for each k-hop anyway, with the sort of way that these interact, and so you can still kind of end up with a kind of different weighting for each k-hop, even if you don't use different weights, separate weights for every k-hop. But yeah, I want to stress that this is not obviously it's not brilliant that it's quadratic scaling. But this was pretty much the first thing that we've done as sort of follow-up work to after publishing the paper. We didn't really have time or space to do it for the actual publication, but the first thing we started working on, and kind of now we have basically addressed this problem and seem to have gotten it down to linear scaling while still keeping the kind of core idea in place. And yeah, you can kind of see that even for this first crack at it, we do have some MPNN versions which do use linear scaling. And still perform well, as we'll see in the experiments later. But yeah, to long-winded way of answering the question, but yes, we still keep the number of connections does grow exponentially as with each layer, which is kind of the point, because we're sort of trying to pose this as a sort of model that falls somewhere in between classical MPNNs and transformers. So where transformers, everything is connected immediately from the very first layer. We kind of have this gradual densification of the computational graph, which allows kind of information to sort of flow more slowly and kind of slows down these like problems of oversmoothing and oversquashing, while still allowing for these long-range interactions to happen.
Yeah, that makes a lot of sense, especially like we know that in many GNN applications, information is very local, right? So even if the graph is very big, there's a lot of information to gather from the locality. So if you connect everything, right, like suppose you have a giant graph that's all of the roads in the US. Well, you don't want to connect directly one road in New York with another one in the West Coast, right?
Yeah.
So you'd like to have it grow like naturally, even if the traveler wants to go from East to West Coast. It makes sense to grow gradually. So I think like this makes a lot of sense. It's scalable, and yeah, lots of information are local, so we want to have this sort of inductive bias added to the GNN.
Yeah, I also this is kind of a suspicion of my own. I can't prove this, but there's kind of this idea that inductive biases are only useful in kind of short-range graph tasks, and they're harmful for long-range graph tasks. And I don't know if that's necessarily the case. It just seems to me that MPNNs, which use inductive biases, don't do very well in long-range graph tasks. And that isn't because inductive biases are bad. How could that ever really be bad? It's just more information. It's because of these problems of over-smoothing and over-squashing that you get as kind of a side effect of using MPNNs. So I'm kind of the opinion that, like, I don't see any reason why long-range tasks shouldn't also benefit from inductive biases. It's just that we haven't really found an effective way with MPNNs or transformers of capturing the inductive biases present in graph topologies in long range, and this is kind of a step towards maybe trying to find that. But anyway, a couple of slides about why Andrew it helps with over-squashing and over-smoothing. So for over-squashing, we kind of base this on the argument from Jake Popping's paper, where they sort of use sensitivity analysis to sort of measure the Jacobian to sort of measure sensitivity as kind of a measure of over-squashing. And they prove that essentially over-squashing occurs because you have these sort of multiplied powers of a normalized adjacency matrix, which exponentially decay to zero. And it's this decaying to zero is the thing that causes over-squashing. And if you kind of write out the Jacobian for, in this case, we're looking at Drew GCN, or Andrew GCN, with nu equals 1. So I wasn't very clear with notation earlier. Essentially, we use like new Drew as just sort of the general thing for any Drew any Drew message passing neural network, and then set nu equal to some number to set the set the amount of delay. So in this case, nu equals 1 is sort of the full delay version. But anyway, yeah, if you look at the simplest case of delay Drew GCN, you could do the same analysis for others, but this is kind of the simplest one. You can kind of see that because you've got all of these extra edges, you have kind of additional terms, some of which, like the one hop terms do decay to zero quite quickly, but you have these additional terms which don't decay as quickly. So essentially, by having these extra layers which are added, these extra edges which are added with each layer, you are sort of slowing down this decay of the sort of effective adjacency matrix and reducing over-squashing. And re-over-smoothing, I haven't really got like a theoretical analysis to prove this, but I think it is fairly sort of obvious intuitively that if you use some form of delay to allow node I and node J to interact when there are hops apart, I mean, if you don't use any delay, I will see J as it is in the current time step, and that will be based on like how many hops apart they are. That will be after a bunch of layers have already occurred, and there will have been some degree of local smoothing already. But if you introduce these skip connections where node I can see node J and it sees it as it was so many time steps ago, then you can see it before this local smoothing even occurs. So in the most extreme case of nu equals 1 or full delay, the first time any two nodes interact is always without any smoothing, any local smoothing, at least from the target node. And then with each subsequent layer, there'll be a little bit more smoothing. But in this way, you're kind of always allowing nodes to interact before over-smoothing happens. So you can essentially, this guarantees that this will go some way to reduce over-smoothing. And yeah, as I sort of mentioned earlier, the choice of delay parameter that you use can be used to control the amount of smoothing. So if you have a high value of nu, then or less delay, then you're allowing nodes to sort of interact more quickly. You get more local smoothing, and information propagates more quickly along the graph, and vice versa for low nu or full delay, where you slow it down significantly. Okay, I'm not going to spend too long on this, but a sort of quick look at sort of some experimental results. So I want to draw general attention to two things. We've kind of got a couple of sort of sets of experiments on real world data sets, mostly the long-range graph benchmark, which consists of a bunch of chemistry and computer vision tasks and covers graph node and edge level tasks. We also have some results on QM9, which I forgot to put into this presentation, so I don't have them visible, but they're in the paper. And sort of separate from the real world. So I'd like to emphasize that those are our real world task experiments in which we are going for performance essentially. And in all of those ones, we make sure to use a fixed parameter budget that is equal to all of the other models that we're comparing against to keep it fair, because obviously we have this quadratic scaling for some of our models. But then below this, we have some not synthetic, but we have some experiments which we're trying to demonstrate particular sort of features of Andrew. So first we have ring transfer, which is a sort of a synthetic long-range task from what paper is that from? The CW Nets paper, which is like synthetic true long-range task, because there's always some debate with a long-range data set whether or not, like, can you even say for certain if it is long-range? This data set is definitely long-range, and it's good for demonstrating the effectiveness of Andrew. And the other one is we have an ablation on one of the tasks from the long-range graph benchmark, where we lift the fixed parameter constraint and essentially go for lots and lots of different model depths and demonstrate like what kind of performance you get with different model depths with different values of nu. But yeah, so maybe it was a bit too much introduction. So yeah, general look at this. We compared Drew with its various sort of vanilla message passing counterparts, and on 4 of these tasks from LRGB, and in all the tasks which span edge, graph, and node level, in all of the tasks, Drew beats its non-Drew counterpart pretty significantly every time. Yeah, I'd like to reiterate that, yeah, this is with a fixed parameter budget, so we're not getting an advantage there. And also, just for simplicity is the only real reason we didn't use any edge features for any of our Drew models. So GCN doesn't use, vanilla GCN doesn't use edge features, but the GIN that we're comparing against and also the gated GCN both use edge features natively. And we still beat it by quite a lot, even though we don't use them at all, which we think is a pretty good example. And we assume that using edge features will improve our scores even more. Yeah, this is a lot, but main things I kind of want to draw attention to. So this is just like kind of all of our results, or we're comparing with various results from the LRGB paper, comparing with a few other kind of static rewiring and transformer benchmarks against the sort of best case Drew models with and without Laplacian positional encoding. Here we've put down the best Drew model based on trying it over different values of nu. Well, we only actually tried nu equals infinity and nu equals 1, and also over different model depths. And the main things I want to sort of draw attention to are that we have these a couple of static rewiring a couple of additional benchmarks. One is a static rewiring benchmark, Diggle, and then we also have mix hop, and we pretty handily beat both of them in all of the tasks. And also want to look at transformers, where so for the sort of more standard graph transformers, just sort of vanilla graph transformer and SAN, we some version of Drew beats these transformers or matches them in all 4 tasks. The only transformer which gives us a good fight is graph GPS, which we still beat it in 2 tasks, 2 tasks out of 4. Do sort of similarly well in the other 2, but I think it's probably worth pointing out here that graph GPS does use, it does have sort of quadratic scaling, which some of our models do, but not all of them. Drew gated doesn't, and it sort of does kind of similarly well. And we've kind of now shown that we can do Drew without quadratic scaling, but also graph GPS combines message passing with transformers. So even though it beats us in a couple of tasks, I kind of see this as a positive thing, because it's combining message passing with transformers. It's kind of arguing in favor of inductive biases and long range tasks. So I think in some ways it kind of supports our claim of use inductive biases better. Okay, yeah, right. So those are our sort of performance things. So yeah, generally good. We beat most other models. Little sort of look at the effect of delay. So this ring transfer data set is a synthetic data set in which essentially you have a bunch of rings of various lengths based on the number of layers of the architecture in order to prevent underreaching. The number of nodes always has to be exactly double the number of layers in the architecture. So this graph could be seen as being number of nodes or number of layers. And the task essentially is that in each ring graph you have a source node and a target node that are one-hot encoded, or rather you have a target node that is one-hot encoded that's on the opposite end of the ring, and the source node needs to learn the one-hot encoded value of the target node in order to, that's the task. And so this is a sort of clear long-range task where as the number of nodes increases, all it has to do is just transfer this information from this end of the graph to this end of the graph without it getting mixed, without it getting over smoothed or over squashed. So we did some experiments with this data, with this task, and we're quite happy to find that you can quite clearly see with this the impact of vDRew and particularly of delay on when applied to long-range tasks. So GCN, standard GCN, fails quite quickly, as is kind of expected. Classical MPNNs are infamous for not being very good when you stack lots of layers. GCN, before you get to 10 layers, which is 20 nodes, completely collapses. SPGCN, which is another multi-hop MPNN, lasts a little bit longer, but still fails, probably because it has lots of many aggregations right from the first layer, so it sort of succumbs to over smoothing more quickly. The graph is like too dense. And then when you introduce vDRew, it lasts even longer. But when you have vDRew with delay, there is no decay in performance, no matter how deep you go, which suggests to us that delay is very effective for long-range tasks, even if this is a bit of a toy problem. And so lastly, we've got another real-world thing to demonstrate, another real-world task to demonstrate the effect of delay. Here we compare GCN against three different choices of delay: nu equals 1, which is full delay; nu equals infinity, which is no delay; and a kind of intermediary where the delay is equals to half the number of layers. And first thing to point out is that any amount of vDRew beats the standard GCN every time for every depth. So suggests that vDRew is generally good, but also you can see here how the choice of delay impacts the performance at different model depths. So you can see that, like, initially, the less delay you have, the better the performance is, because with fewer layers, like 5 layers, you are allowing the information to propagate sort of more quickly. You have fewer layers in which to do it, so you kind of need that faster propagation. Whereas if you let it go quite deep, like 20 plus layers, you can see that the full delay version goes up to being the best one, because of this like slower propagation of information. It is sort of worse to begin with, but it can do well over lots and lots of layers, where a standard MPNN would likely fail. So this is sort of just to demonstrate like how you can use this choice of nu to kind of affect like how fast you want information to propagate throughout the graph, and so as a result, how you can choose it based on your task. So if you know that you've got a very big graph and you need lots and lots of layers for information to propagate, or you kind of just want to slow information propagation down, then you can choose nu to sort of suit that need. I've just noticed there's a bunch of questions in the chat. Okay, I will. Oh boy. Yes, okay, there's a couple on ring transfer, so I'll jump back and do those. How does transformer-based models perform in ring transfer? Yeah, I haven't done this test and I haven't seen it. It's possible that it would do fairly well, but I don't think that necessarily. I think they probably would do quite well, but also they would do it with, I guess, more scaling, and it's kind of a really big hammer for a fairly simple nail. What delay was used for ring transfer? For those experiments, we use various choices of delay. We have nu1, which is full delay, and then vDRew GCN is just nu equals infinity, so that's no delay. You have any insight on why delay works so good for ring transfer? Well, that would be, I mean, essentially because you're allowing nodes to interact before local smoothing happens. Because, you know, if you have to stack lots and lots of layers, the nodes will definitely over smooth and the information will be lost. They won't be able to propagate over like lots and lots of hops. If you allow these interactions to happen between distant nodes before this over smoothing happens, then the nodes can interact with each other. I think it's sort of as simple as that. And yeah, that's basically it. So sort of some future directions of work. I haven't talked about it at all here. We do a very limited exploration of this in the paper, but so interesting to look into expressive power, reducing parameter scaling to subquadratic or to linear, which is we've basically making pretty good progress on this already. We would like to sort of be able to concretely measure that we are definitely mitigating oversmoothing and oversquashing. So far, we have like pretty decent evidence, I think, empirical evidence that this is happening. But it would be good to be able to directly sort of measure these using maybe like the Jacobian or using Dirichlet energy for oversmoothing to just verify for certain that this is actually what's happening. We're also kind of interested in using alternate distance measures to just the sort of hop geodesic distance, like maybe like random walk or something to do with clustering or something like that. And then lastly, we're kind of interested in extending the idea of delay to attention, or particularly to transformers to global, global MPNNs. And yeah, that's all. So yeah, if there are any more questions, I think I covered some of that. Yes, Andre.
Hi. So yeah, thank you for your talk. Super interesting. I've actually seen the paper previously, and a thing that was very interesting for me was a figure in your appendix, I think, in which you show that Drew scales very well with the number of layers. Do you have any kind of intuition regarding this? Like, do you think it's maybe easier to optimize because maybe you mitigate stuff like vanishing gradients, or do you think there's something else?
I'm not sure. Yeah, we wondered about vanishing gradients. It's not something that we talked about, sort of talked about in the paper. It's kind of something we thought about after it was published. So it may be that is a factor. And this is kind of, you know, I was saying like we would like to investigate like what are the actual factors that are causing this effect. Like, is it mostly over smoothing or over squashing or vanishing gradients or what? But in terms of like intuition of why this is happening, I mean, I think it, to be honest, is let me think about this. I mean, I think it's just sort of a. I mean, I think it's kind of just due to this thing we're doing of like slowing down the information flow. You know, like we have these distant connections that don't necessarily have a lot of oversmoothing between them. Then even as the layers get deep, you're still going to be seeing nodes, or nodes are still going to be seeing other nodes that haven't been oversmoothed at all. So if you take the oversmoothing perspective, that would, you know, definitely, you know, give it more longevity in terms of doing better as you stack the number of layers. That combined with, I think, just the sort of greater expressive power of like doing multi-hop, because this is ultimately a multi-hop MPNN, I think is probably it.
Yeah, that makes a lot of sense. Thanks a lot.
No worries.
Yeah, thanks a lot, Ben, for the great talk. It was very interesting to see all that, and I had already discussed this project with Francesco prior to your presentation, so it's nice to being reminded of the work.
Thanks very much.
One thing, one question I would have, like for example, with this figure that you're showing here is GCN is probably the worst model in terms of oversmoothing. And I was wondering, like, if you would see benefits similar to what you see here, but using Gini, for example, or gated GCN, and whether you can see that increasing the number of layers will also improve the performance, or not.
So yeah, I don't have a decent plot for this because essentially ran out of time before the deadline to sort of look at do this same ablation for other data sets and for other Drew models. But yeah, like that is the suspicion that you will have a very similar effect. I mean, the framework is basically the same, and I don't think that you'd really expect GIN or gated GCN to do any better when you stack the number of layers. They're ultimately still still kind of smoothing convolutional NPN, well, not gated, but sort of still convolutional smoothing MPNNs. Yeah, I do suspect that probably you would get a similar thing, but I haven't got results for it. You do see that, like, as you, depending on the choice of delay, you do sort of clearly get better results with higher. What am I trying to say here? The more delay you use, you tend to get better results with larger layers, which I think sort of suggests that definitely there is I think that suggests more than anything that there is definitely like long range interactions being captured. Like if you need like 20 or whatever layers and you're using full delay such that two nodes can only interact directly after 20 layers, then that's kind of almost proof that like there is some definite benefit that you're getting from long range.
Yeah, I think one of the very, very simple methods that people use to mitigate this long-range information propagation is adding a virtual node that's connected to every other node at every layer, right? So that basically, let's say every layer, you pull everything and then you concat to every node.
Yeah.
And this is known to help mitigate over-smoothing, although like it's smooth. Like the bigger the graph, the harder virtual node would be, I presume. And it would be great like to have a curve also like there where GCN with virtual node to really show that, hey, Drew is like much better than what virtual node and traditional methods of overcoming the information bottleneck in graphs.
Yeah, I mean, it's interesting because I get this sort of adding a global node. I mean, is essentially very similar to just like connecting everything. I mean, you're just making everything connected by 2 hops rather than making everything connected by 1 hop. And it's annoying. We had a table for like looking at QM9, which has a bunch of MPNNs on it with like an extra fully adjacent layer added, and we beat those. But yeah, I forgot to I didn't have time to put it into this presentation.
Yeah.
But yeah, I guess that fully.
That's perfect.
Yeah.
Also you mentioned in your future work that like you'd like to combine Drew with transformers, but isn't that just like taking gated GCN or GAT as the model that you work with Drew? Gated GCN uses a sigmoid instead of a softmax, but it's essentially like attention. And GAT is also essentially attention. So like, what do you mean by combining Drew with attention if it's not just taking GAT?
Sure. So yeah, there's kind of 2 ways to look at this. There's the way, as you sort of said, where it's essentially just another form of, kind of similar to gated. I mean, it's effectively just extending Drew to more different MPNNs, but this time sort of using the kind of attention, sort of same kind of attention setup. But probably the slightly more interesting one we haven't really started working on, but I'm keen to, is like trying to apply delay, not so much the dynamically rewired part because it doesn't really work, but applying delay to like global graph transformers, and possibly you have to, it's quite a different sort of setup, and you wouldn't be able to have as many layers, for instance. It would still have to be like probably quadratic parameters wise, but like sort of coming up with an alternative measure of time, like potentially having some kind of varying like weights over previous time steps, potentially having like different kind of attention heads over different delay parameters is something we've talked about, which I think would be quite interesting. So yeah, we haven't really started properly with doing this, but we've got a few kind of ways that we thought of about potentially introducing delay to global graph transformers.
Okay, cool. Yeah, that sounds super interesting. Looking forward to see that work. All right, so
yeah, me too.
Yeah, let's go to Dennis's question.
Yeah, thank you. Maybe last question. Is there maybe a way to sort of choose new and the delay parameter dynamically, because I suppose that for some kind of logical tasks, it should be sort of very discretely defined, very precisely defined, and obviously in a large graph, especially like in knowledge graph, there would be very different conditions for different entities in terms of the required delay. And also I was thinking about maybe that this can allow you to use something akin to truncation in PageRank, because when the diffusion is propagated on the nodes, you usually can truncate sort of connections that oversmoothed. So maybe here you can also during the training see what interactions tend to get oversmoothed and maybe somehow adjust delay to them.
Okay, so read the first point. I agree that yes, it's probably a sort of downside of the model. Well, you can see it as a strength in terms of its sort of ability to sort of choose new for particular tasks. But obviously, yes, it is an additional hyperparameter that you need to figure out. And what we've done so far is just do it by sort of trial and error. Fortunately, we only really are looking at either full delay or, well, mostly we've looked at either full delay or no delay. But yeah, like this is something that is not ideal, and it would be good to have a kind of more principled way of determining this, which choice of this delay hyperparameter would be best. And I think our main way that we're probably going to try and address this is to, probably have some kind of either sort of incorporate it into like the training or introduce some kind of like attention where we like have multiple different delays and kind of allow sort of attention over the different ones. I like that one better, so I might do something like that. As your second point, I didn't really catch all of it there. I had a bit of distortion for a minute there, and I'm not super familiar with truncation or page rank, so I'm not sure how well I'll be able to answer anyway. But
yeah, okay. It was a rather loose analogy. I just basically wanted to illustrate that during training you may observe that some I would say that some nodes, some connections like hop connections tend to be very oversmoothed because well, you can actually in the paper you was I think it was mentioned that we used some node similarity measure, but I haven't noticed that you mentioned it during your talk. But in general, using some nodes similarity, you can probably find which nodes tend to get oversmoothed. Obviously, they probably will be like high degree nodes or something like that, and you can try to position the account for them with increased delay.
Yeah, we wanted to look at sort of Dirichlet energy as a way of sort of measuring over smoothing, but it didn't end up panning out before the paper deadline. So that's something we would like to do. And yeah, I guess other methods like looking at degree to sort of determine which nodes might be more oversmooth is something that we could do as well, I suppose.
Yeah. Okay. Thank you. Thank you.
Thanks. There's one other question in the chat that I've just seen, which is the Jacobian metric a standard metric to measure over squashing? As far as I know, yes. I mean, it's from this paper by Jake Topping from a couple of years ago, and I think Francesco and the collaborators have just put out another paper which is doing a proper deep dive on over squashing. It's definitely the best sort of deep dive in over squashing and what causes it and measuring it that I've seen. So yeah, I would say that probably Jacobian probably is the best metric that at least that I know of. Yeah.